All right, welcome. Today we're going to get a handle on a seriously powerful tool in trigonometry, the double angle formulas. Seriously, these things are like cheat codes that can make really complicated problems suddenly click into place.
So let's just jump right in with a question. Say you know the sine of some angle, we'll call it theta. How in the world would you find the sine of twice that angle, of 2 theta? Is it really as simple as just multiplying by 2? Spoiler alert, nope, not quite. But the real answer is way cooler.
And here's the best part. You don't even have to learn this from scratch. If you remember those sum and difference formulas, well, you're pretty much all the way there. These double angle formulas are really just a clever shortcut using what you've already learned.
Okay, let's pull back the curtain and see exactly what these formulas are, and, more importantly, where they come from.
First up is the sine double angle formula. So think back to the sum formula for a second. Sine of alpha plus beta. Now, what would happen if alpha and beta were the exact same angle? Let's just call them both theta. Well, you'd get sine of theta plus theta, which simplifies right down to this beautiful, clean formula. Sine of 2 theta equals 2 sine theta cos theta.
And guess what? The tangent formula follows the exact same logic. You take the tangent sum formula, you make both angles theta, and boom, it cleans up perfectly into this expression right here.
Now this is where it gets really interesting. Cosine is kind of special because its double angle formula comes in 3 different flavors. This first one, cos squared theta minus sine squared theta, should look really familiar. It's almost the Pythagorean identity, but notice that supercritical minus sign. That one little change makes all the difference.
And check this out. This shows you exactly where the other 2 forms come from. You just take that main form and you use the good old Pythagorean identity to substitute. You can swap out the sine part to get a version with only cosine, or you can swap out the cosine part to get a version with only sine. It's like having a Swiss Army knife. You can pick the perfect tool for whatever problem you're facing.
Okay, knowing the formulas is one thing, but putting them to work is where the magic really happens. So let's stop talking theory and actually solve some problems.
All right, let's start with a classic. We're given the sine of an angle, we know what quadrant it's in, and we need to find the sine of twice that angle.
Okay, let's break this down. The formula for sine of 2 theta needs both sine and cosine. But wait, the problem only gave us sine. No problem. First step is to use the Pythagorean identity to find cosine. Since we know theta is in quadrant I, cosine has to be positive, so it's 4/5. And now we have all the pieces. We just plug them into the formula, 2 times 3/5 times 4/5, and that gets us our final answer, 24/25.
Let's try another one. This time, it's not about plugging in numbers. It's all about pattern recognition.
When you see an expression like this, cos squared x minus sine squared x, a light bulb should go off in your head. That is the literal textbook definition of the cosine double angle formula. So the simplified answer is just cos of 2x. That's it. It's a perfect example of how these identities let us take something that looks complicated and make it super simple. Okay, time to level up. For this one, we're going to use the formula to help us solve a trigonometric equation. This is where these identities really start to flex their muscles.
So the big issue here is that we have mixed angles, a 2x and an x. You can't solve it like that. So what's our first move? We use our new formula to expand sine 2x into 2 sine x cos x. Now we're getting somewhere. We can bring everything to one side and factor out that common cos x term. What this does is break one hard problem into 2 much easier problems, and solving each of those gives us our 4 final answers.
These formulas are awesome, but like any powerful tool, there are a couple of common mistakes you really got to watch out for.
Okay, the number 1 most common mistake, hands down, is forgetting the 2 in the sine double angle formula. It's so easy to just write down sine theta cos theta and move on, but that 2 out front is absolutely critical. Don't forget it. And for cosine, you need to work smarter, not harder. I mean, why calculate something you don't have to? Look at what the problem gives you. If they only give you sine, use the sine-only version. If they only give you cosine, use the cosine-only one. Choosing the right tool from the get-go saves a ton of time.
So you might be asking, okay, this is cool and all, but is it just a math trick? Am I ever going to use this? Oh, absolutely. Let's look at a real-world application.
Think about it. Anytime you throw or launch something, a baseball, a cannonball, whatever, it's a projectile. And the physics formula that describes how far that object is going to fly has our good friend, sine 2 theta, right there in the middle of it.
So how do you throw that baseball for the maximum possible distance?
Well, you need to make that sine 2 theta part of the equation as big as possible. We know the biggest value the sine function can ever have is 1, and that happens when its input is 90 degrees. So if 2 theta has to be 90, then your launch angle, theta, has to be 45 degrees. It's not a guess, it's not a theory, it's pure math. That's why athletes work so hard to hit that perfect 45-degree angle.
Here's the big takeaway I want you to have. These formulas are not just another thing to memorize for a test. Think of them as a bridge. They're the connection that's going to carry you from trigonometry into calculus. Because when you get to integration, you'll find there are some problems that are basically impossible to solve without them. Getting these down now is going to pay off big time. So, we figured out how to take an angle and find the trig functions for double that angle. And that leaves us with one final thought. If this is how you make an angle twice as big, how would you go in the other direction and cut one right in half?